Hello, in this video we're going to deal with other techniques of solving differential equations, in particular the technique for solving linear differential equations, for which we use a technique called the integrating factor. So I wanted to use this with you, and to do so I need you to consider the product rule for a minute, because if you think about it, when I have something like this and I differentiate both sides, I'm going to end up with this expression, right? I'm going to end up with this expression has no differentials, and I'm going to end up with this expression with a differential. Now, if I see this kind of situation at some point, I might already realize that I can backtrack to this, right? I can't see this at one point. This is the exercise, and perhaps I should have the skill of realizing that this can turn into this. So if that's the case, if I have to be able to realize, well, it's not going to be that easy. It really is not going to be that straightforward to know how to do this the other way around, to realize that I have this product rule going on, especially because not only we're going to be looking for this situation, but also we're going to kind of create it, because it's going to be a powerful differential equation solving technique. So in general, what we're going to be doing is we're going to be looking for equations that have the following form. Now, you're going to have the differential or differentials, and then you're going to have an expression of x, whatever they want, whatever you need, times y, and only y. I mean, not y squared, or not like dy here, like just y. And that's going to be equal something with x's. Now, if you have the situation, you're in luck. You can use this method. Note, however, that maybe there's an expression of x here before the differential. I can just transfer that to the rest by multiplying by 1 over that expression, and it will disappear here, become a 1, and here I'll just have a different expression with x, and here I'll have a different expression with x. So equations in this form are called linear differential equations, and I'm going to explain to you what the technique is for solving. So first of all, let's think about what this integrating factor is going to be and how it's going to help us. Now, this integrating factor comes from the following idea. If I have the differential equation in this form, and if I multiply both sides of the equation by a function ix, and I know, and this is how I define ix, this is not a coincidence, just because this is how I define it, such that I prime of x, the derivative of the function, is I of x times p of x, right? If that's the case, then when I multiply both sides of the equation by this, I'm going to end up with the following expression. Now, the advantage is that already you should realize that because ix is here and ix is here with the px, what I have here is I prime of x. And hence, I have the derivative of the second one with the y plus the derivative of the first one here, because this is I prime of x. So this expression, I'm going to be able to just write it in this way, right? Because I know that this is the derivative of the product, hence the derivative of the product. And by integrating both sides, I'm going to end up with being able to leave the y alone on one side of the equation. So this is how I'm going to be able to solve the linear differential equations. I find the y prime of x. I define an ix such that the I keep saying y, I prime of x is equal to ix times px. I define it that way, and when I multiply both sides of the equation, I can write it as a product rule. I can write it as the result of a product rule, and hence I integrate both sides, and I can just separate the variables now and find the solution, the general solution of the differential equation. So this ix, this integrating factor, how do I find it? I need an ix such that I prime of x is equal to ix times px, right? So how do I find that one out? Well, this is my definition. So if I just solve this equation, I can reshuffle it and integrate both sides. And of course, what I'm going to end up here having is that the natural logarithm of I of x is equal to the integration of p of x. Now, I don't know what that is. But important thing is that now I can just write that I of x is going to be equal to e to the power of the integration of px dx. And this is the integrating factor, and this is in your formula booklet. So you don't have to memorize it, but I really recommend just understanding where it comes from. It's not that complicated, just one more slide. So I think it's worthwhile. Now, this is all a lot of information. How do I use it? Let's go start with an easy example. So here's a differential equation, right? Now, in this case here, p of x is 3, simply 3, just a 3, right? It's that thing that's multiplying to y. So the integrating factor is going to be e to the power of integration of 3 dx, which is going to be e to the power of 3x, right? That's my integrating factor. So I multiply both sides of the equation by it, and I'm going to end up with the following expression. Now again, here I have a product rule. I know here that I have the derivative of e to the power of 3x times y. So I write it that way, and now I integrate both sides, and I end up with the following expression. And now y is just going to be equal to 1/5 times e to the power 2x plus c times e to the power minus 3x. And that's it. And that's how you do it. Let's do a slightly harder example. Here's some trigonometric functions. So again, here, remember I told you at the beginning that if you have something here, you can just divide everything by it. So if I multiply everything by 1 over cos x, I end up having my equation in the linear form. And now I just do it the same way. Calculate the integrating factor. There you go. Come back to the following way. Because simply e to the power of a natural logarithm, well, it's just going to be whatever you have inside the natural logarithm. And now I just multiply both sides of the equation by that. And hence I end up with, again, my product rule here. So at least to see it's a product rule, but just take your time to see it. You can assume it's going to be that way because that's how beautifully the integrating factor works. I integrate both sides, and hence I end up with the following expression and with my general solution. And that's it. That's how you use the integrating factor, how you solve linear differential equations. Requires practice, quite a bit of practice, but again, it's just procedural. So I think you will be able to get it quite well. Thank you very much for watching. I'll see you next time. Yep, there's a bit more information here. I'm sure you don't mind. But anyway, bottom line is you are done with solving differential equations. Now you have the estimating differential equations, Euler and Taylor. These are perhaps slightly harder. These are the other ones who are quite procedural. Thank you very much for watching again. Goodbye.